Hello, everyone. This is section 4.4, and this section we'll be talking about um, curve sketching techniques. So here, well, I see lots of dots here. Anyway, so in this section, yeah, we will be following all these steps to find to sketch the graph of f of x. All right, so basically, if you see all of these things, we have already followed or we have already learned these things, and I think I have followed all of these process to get the sketch of f of x. But in this section, the function f of x will be a little bit different. It will be a fraction, or maybe with e, we will be dealing with e and stuff like that. All right, so okay, so the first step, the f of x will be given, and from f of x, I can find the domain of that function. I can find y-intercept and x-intercept of the function. I can also find the horizontal and vertical asymptotes of the function if they exist, right? And similarly, still on step 2, I can get the first derivative of f of x, and from the first derivative, after we get the first derivative, I can find the critical numbers, increasing, decreasing intervals, local maxima, minima, by making the sign chart. Similarly, from step 3 or using step 3 here, well, I can find concave up, concave down, inflection point using f double prime. And once we do all of these, at the end, I can sketch the graph by using all of these things that we get from all these from step 1 to step 3. All right, so now let's start. Okay, so let's see this example first. Okay, now this will be given. Okay, this will be given, the problem, and then after that, we need to find all of these. Okay, so the domain, since we have a fraction here, so whenever we deal with a fraction, we have to make sure that the denominator is not 0 when we are trying to find the domain, right? So that's why here, this denominator, x minus 3 is equals to 0, so x is equals to 3. So the domain will be everything else except x is equals to 3, or except 3, all real numbers, right? All real numbers. For the domain. For y-intercept, to find the y-intercept, we assume x is equals to 0, right? So if we assume x is equals to 0 from this function, then I can find y-intercept or f of x, right? So y is equals to x is 0 plus 3, 3, and basically we just plug in this 0 to this equation, and then we get y is equals to -1. So from there, I can change this to a point form. Y-intercept is now 0, -1. Similarly, I can find x-intercept. In this one, we assume y is equals to 0, and then we assume y is equals to 0, means this will be 0. So 0 is equals to x plus 3 over x minus 3, and then multiply both sides by x minus 3, right? So that way, this is gone. So we just have x plus 3 is equals to 0, and x is equals to -3. So x-intercept is -3, 0. All right. And similarly for vertical asymptotes, so for the vertical asymptotes, first, whatever the function is given, we will try to simplify this, right? So we have to simplify the given function. But the thing here is this function is already simplified. All right, so there is no, we cannot simplify anything further from this point. So that's why after, after you simplify the function, then we will again take the denominator just like we did for the domain. But the domain, you just take whatever the original equation is, and then just take the denominator is equals to 0. So that value is not possible for domain. All right, now for vertical asymptotes, we have to simplify, and then after that, we take the denominator. But since this is already simplified, like I said, right? So we take the denominator, and then from there, this is the vertical asymptotes. All right. So yeah, you need to know this idea. All right. So I see most of you guys make mistakes on these kind of thing. Okay. And similarly for horizontal asymptote, we have to see the degree of the numerator. So the degree of the numerator is 1, degree of this, degree of numerator is 1, degree of denominator is also 1. So if the degree of denominator, if the degree of, let's say, numerator is equals to degree of denominator, we learned this in chapter 1, right? And I think I've asked similar thing in the exam 1 as well, right? If these two are, the degree of these two are same, then we take the coefficient of that terms. So here is 1, here is 1. So y is equals to 1 over 1. So we divide the coefficient of this by coefficient of this, right? So since both of these are 1, so that's why we get y is equals to 1 for horizontal asymptotes. Right, so now, so this is the step 1. So for step 2, I have to take first derivative. So let's go to the next page for that. So since we have f of x is equals to x plus 3 over x minus 3. So now when we take the derivative of this, so when we take the derivative of this, then it will be, first we have to take the derivative of the numerator, right? So this denominator will be the same times the derivative of the numerator. So I see that some of you guys wrote, like, when you write f prime, I see that still some of you guys write x minus 3 times x plus 3 here. So when you take the derivative, now you cannot write this here, because this is not the derivative of f of x. So if you want to write this, you have to write the prime sign here. So that way it shows that, okay, you are taking the derivative of x plus 3. All right. Because I see some of you guys, let me write the whole thing. I see some of you guys write, okay, so maybe you're thinking, okay, I'll be taking the derivative of this, right? So maybe that's your thinking, but in math, it's not correct. You cannot just write it like this. So x minus 3 times taking the derivative of the numerator minus, now the numerator will be the same, and times denominator over x minus 3 square. I saw that some of you guys wrote something like this, but you are missing this part, this prime. If you want to write it like this, okay. But anyway, all right. So okay. So anyway, let's find the derivative of this. So x minus 3 times, now when you take the derivative of numerator, x plus 3. So when you take the derivative of x, this is just 1. And the derivative of 3 is 0. So that doesn't make any difference. Minus, now numerator will be the same. And then take the derivative of denominator. Again, it is 1, right? So 1 over x minus 3 square. And then from here, well, it looks like, well, in the first here, it will be the same x minus 3, but there is a minus here. So when you distribute this minus to these two, because this 1, this times 1 will be still this thing, x plus 3. So when you distribute this, it will be negative x, negative 3 over x minus 3 square. So here I can cancel positive and negative. negative x, so this will be negative 6 over x minus 3 square. Okay, so now after this, okay, so how do we now, once we get this, well, first we need to find the partition number, and we need to figure out if that partition number is a critical number or not. All right, so the partition number is basically a number which will not, since we are dealing with a fraction, right? So when we are dealing with a fraction, now we have to see what value of x is going to make this f prime of x undefined, because we know that this is f prime of x, right? So what value of x is going to make this f prime of x undefined? So if we take x is well, x is equals to 3, this will make this denominator 0, right? Because 3 minus 3 is 0, 0 squared is still 0. So this will be a number negative 6 over 0, which is undefined, right? So, and then once we get the partition number, then again, I have to take this partition number and see or check if this x value is going to work for f function or not. If this value works for this f function, then we can say that this number is a critical number. But well, when you say this, when I say this x is 3, and when I plug in this to this equation, I get f of 3 is equals to 3 plus 3 is 6 on the top, and on the denominator we get 0, right? So again, this is undefined. So this means this is not a critical number. So in this case, there is no critical number. All right. So now after this, what we can do is, okay, so now we can make a sign chart, and well, this is a partition number, but this is not a critical number, right? Now, I have to find which side is going to be positive and which side is going to be negative. Now, when I pick any point on this region, let's say x is equals to 0, and plug this into f prime, right, to find if you get positive or negative. So if I plug in this to, so this is f prime, right? So if I plug in this to this, so x is 0, so we still have this negative 3, so negative 3 squared is positive, but we have a negative on the top, so that way we'll get negative here. All right, you can do this part on your own to figure out, but yeah, this should be negative. All right. And similarly, on right hand side, I can pick any point. Let's say x is equals to 4. So if I pick 4 and plug it in here, then 4 minus 3 is positive. So positive square is a positive, but still we have a negative on the top. So this will be a negative number. So it looks like both of these are now, if there is a negative, it's decreasing, right? Let me just write DEC, decreasing. And also this is decreasing. So since this is decreasing, so maybe I'm just saying, maybe it will be, I don't know, it will be something like this. I don't know, something like this, decreasing, something like this, right? It's decreasing. So if both of these are decreasing, then we cannot find local maxima or local minima, right? Because yeah, both of them, well, only time we can find that local maximum or minimum is if there is a sign change, right? And also, yeah, this point is not a critical number, so we cannot include this point to this point. But anyway, so we can say the decreasing interval, let's say decreasing interval is from negative infinity to 3, and also from 3 to infinity, right? And there is no increasing interval, so we don't have to do that, and no local max and min, right? All right, so now that's all for f prime. Now let's go to f double prime, and let's take f double prime first. So f first prime is -6 over x minus 3 square, right? We found that from this here. Now when we take f double prime, well, I can also say this is same as if I move this x minus 3 to the top, then it will be -6 x minus 3 to the power -2, right? So now I can take f double prime, which will be, okay, this will come down here when we take the power rule. So -6 times -2 times x minus 3 to the power of this -2 and -1, right? So this will give 6 times, -6 times -2 is +12, x to the power, x minus 3 to the power -3. So this will be 12 over x minus 3 to the power +3. All right, so from here now, again, we have a fraction here. So same thing we did here for a critical number. We have to do the same thing here for inflection point. So I can find the inflection point from this f double prime, right? So well, again, it looks like when I say x is equals to 3, then this will make f double prime undefined, right? So if x is equals to -3, it will make f double prime undefined. So this will be, well, this is not yet the inflection point. We have to see if this is going to be inflection point or not, but this is a partition number. So similarly, I can take this x is equals to 3 to the original equation. So what is the original equation we had? Our f of x was x plus 3 over x minus 3, right? So if I say x is equals to 3, then a similar thing we did here, right? So it will be again undefined. So that's why this is not an inflection point, because we get this undefined if I say x is equals to 3, right? So again, there is no inflection point. All right. And here, let's say, again, I can say 3 is somewhere down here. Now I can pick any point on this side and plug this. Again, I can say x is equals to 0, plug this into this f double prime and see if you get positive or negatives. In this case, we will be getting this negative. And here, if I pick any point here on this side, it's x is equals to 4, plug this into this equation again, and we'll get this positive. But well, here we have a sign change, right? And technically before we said that if we have a sign change, then we can say this is an inflection point. But here, since this point, if I use this point to this f of x will get undefined, right? So that's the reason we cannot say this is an inflection point. So that is the reason, right? That is the point we're saying this is undefined. And yeah, this idea is very important for the exam. So I might ask something like this. Okay, so for exam, you definitely want to review this kind of thing. These kind of idea. Why this point is not inflection point, even though there is a sign change, right? Okay, so now once we have everything here, now the last thing is to get the picture or to sketch the graph of f of x. All right, so here first, okay, now to get the graph of these things first, sketch x in a horizontal asymptote and vertical asymptote. So from this here, well, yeah, the vertical asymptote is x is equals to 3, horizontal asymptote is y is equals to 1, x is equals to 3, and y is equals to 1. So x is equals to 3, so 1, 2, 3, so x is equals to 3 will be the vertical, this is a vertical asymptote, so it will be a vertical line, something like this, that goes through this 3, and horizontal asymptote is y is equals to 1, so a horizontal line, something like this, right? And then okay, so, and then x-intercept and y-intercept are given as well. So y-intercept is 0, -1, x-intercept is 3, 0. So y-intercept is 0, 0, -1, and x-intercept is -3, 0. So let's plot this point. So 0, -1 is somewhere down here. -3, 0 will be -3, 0 is, let's say 1, 2, 3, so somewhere down here. So our graph would look something. So as we said, this is a horizontal asymptote, so there will be a line that will be approaching towards that. So this is not a perfect graph, right? But it will look something like this. There should be a curve. And similarly here, since we have this graph here, so it should be something like that here as well. Well, to find these points, you can pick any point, any point on the right from, this is 3, right? So if I pick 4, you will get some point somewhere down here. If I pick 5, you'll get some point somewhere down here. So you can do that, but if you're getting something like this here on the left hand side, you should get something here on the right hand side too. And also here, well, this is a concave down, right? So as we see that on this left hand side, we're supposed to get this concave down because there is a negative here and there is a positive here, so concave up, right? So that's why we have a concave up here as well after 3. So this is after 3. All right, so we're using this idea as well. So this is concave down, so that's why this is concave down, this is concave up, this is concave up. And yeah, that's all I want to talk about for this problem. And also you can write concave down interval, which is -infinity to 3, and concave up interval, which is 3 to infinity. All right. Now the second one, I won't be doing everything like I did here. So I will be just doing a first step of this this strategy. This step 2, step 3, step 4, you can do this on your own. Well, this is still not a quiz problem, but you can do those problems just for practice. All right, you don't have to submit that. All right, so you don't have to submit those. Let me just do But let me just start this first at least. Okay, so here first, the domain, right? Step one, I have to find the domain. So the domain will be all, well, here it looks like, well, there is no fraction here. There is no square root here. So in this case, it looks like all the value of x are going to work here. It doesn't matter whatever you pick here. All real numbers are going to work. So you can say from negative infinity to positive infinity, something like this, or you can just say all real numbers. And the second one is y-intercept. Let's y-intercept, and we can find y-intercept if x is equals to 0. So then I can say that from here, y is equals to 0 times x to the power, 0 times e to the power 0 is equals to, well, this part is 1, e to the power 0, or any number to the power 0 is 1. So 0 times 1 is still 0. So that means the y-intercept is 0, 0. So if y-intercept is 0, 0, then I can automatically say that this is also x-intercept, right? If you have a graph, something like this, if this, let's just say a random graph, if we have a graph something like this, if this goes through 0, 0, then I can easily say that this is also x-intercept point. And well, and it looks like for this equation, well, there might be other graph which might just go like this as well, and there might be another x-intercept. But here in this case, since we have these kind of graph, E, right? So if we have an E, then the graph would be, and we are saying that this is, well, it's going to go through 0, 0, so it might be something like this. So there is no other x-intercept point. All right. So these are both x-intercept and y-intercept both. Okay. And for a vertical asymptote, well, there is nothing. The reason for this is, again, well, since we have an E, so the graph would be something like this. So the vertical asymptote means, well, this is going towards infinity. So there is no vertical asymptotes, means a vertical asymptote means there is a line which is not going to be touched by this graph, right? So there won't be any line where graph is not going to touch, because this is approaching towards infinity. So that's why there is no vertical asymptote. And for horizontal asymptote, it's a little bit tricky, but it's not that tricky as well. For horizontal asymptotes, so for horizontal asymptote, well, it's a horizontal line, right? We have to find a horizontal line where this is never going to touch, right? So let's analyze this saying, okay, let's say if x, well, we know that this is going towards infinity. So if you see on the right hand side, if I say x is going towards infinity, if x is going towards infinity, or I can say, I can introduce a limit where I can say x goes to infinity on this function, x is equals to e to the power x, to analyze this right hand side part. All right, first I'm going to say x goes to infinity and see where this graph is approaching. If I say x goes to infinity, it looks like, okay, here it will be infinity times e to the power infinity is infinity. So if x goes to infinity, this will goes to infinity. Now let's analyze where it's going to go to. X goes to negative infinity. then it looks like, well, I can write this in the limit style. So x goes to negative infinity of x times e to the power x. So it will be something like, okay, so when x goes to negative infinity, it will be negative infinity times e to the power negative infinity, which is same as negative infinity over, so there is a negative here, so I can move this to the down, it will be e to the power positive infinity, right? So this way I can say on the top, we still have negative infinity over positive infinity. So technically this is infinity over infinity, which, well, in this case, now I can use L'Hopital rule that we learned in section 4.3. Right, so that means I can take the well, if this one goes to yeah, if using L'Hopital rule, I can say, okay, now I can technically write this as e to the power x over e to the power x over e to the power x. The reason is this is going towards negative. So from here, now I can take the derivative of the numerator, which will be just 1. The derivative of denominator, which will be e to the power x, still e to the power x. Now I can take the limit of this. Okay, so after I taking the limit of that, limit x goes to negative infinity. Wait. I think I did a mistake here. Sorry, this is not correct. Let me go back. I think it's easy if I write it on. So we are taking, or we're using the L'Hopital rule of this, right? Right. So let's do this. Sorry. Yeah. Let's take let's use the product rule of this, because now wait. I can't even use the product rule here. Just give me a moment here. All right. Let me just pause it for a few seconds. All right. Yeah, I'm back. So here, the idea here is, well, let's go back to this. So as we said that here we get negative infinity over e to the power negative infinity, right? So from here, I can say that, well, on the top, well, if x goes to infinity or negative infinity, this x will be negative infinity on the top, right? And on the bottom, it will be e to the power positive infinity. But the thing is, this e to the power positive infinity, this one is much bigger than this thing on the numerator. All right. The reason is, when I say x, because this exponential, the graph of this exponential function means when I give some value of x, the y is going to be much bigger. That's the nature of this graph, right? And if you try to input this on your calculator as well, if you pick e to the power something, let's say a big number, let's say 1,000, or let's say a billion or something like that. You can see this from a Google or something like that, just to check it, it will be a much bigger number, big number, all right? And x here on the top, we say x is 1,000, right? So 1,000 divided by a big number, really big number, will be, so something, a small number, let's say 2 divided by a really big number is approaching towards, let's say 2 to the power, or 2 over a big number, let's say 0.000000. It will be something like 0.00002. So this number I can technically, in this case, I can say that this number is same as 0. All right. So here, that's why we get this 0, just because that this e to the power infinity is much bigger than this thing on the top. All right. And the rest of the part, like I said, step 2, step 3, step 4, you can just do this on your own, just for the practice, but this is not the quiz problem. All right. All right. Yep, I was a little bit confused on this last part, but anyway, I hope you understood this. And if you still have any questions, you can ask me during the office hour as well. All right. Okay, I'll see you in the next video. Thank you.